Hi, and today we are going to study the concept of absorption. So, we are going to study the concept of absorption, and mainly we are going to focus on the designing in the number of trays. Okay, this is regarding the designing of number of trays required. And now in this case we are going to assume that when ammonia, which is present in air, and this ammonia is considered as component A and air is considered as component B, and we are going to absorb this ammonia by making the use of water, which is called as component C. So mainly absorption is practiced in countercurrent process. So if you draw the diagram of this absorption tower, and we are going to deal with the designing of the number of trays. So if we represent this trays like this, so this will be GNP plus 1, that is the total amount of the gas mixture which is entering the absorption tower. And if this has the mole fraction YNP plus 1 of ammonia, and this is our water, so we'll denote it by L0, and if X0 is the mole fraction of the ammonia which is present in this water stream, and here the leaving gas, we'll call it as G1, and suppose Y1 is the mole fraction of ammonia at the outlet of this gas, and here we have L and P, and the mole fraction of the ammonia which is present in the stream is given by X and P. And now what we are going to do is, if we take the mole balance, if we take the overall balance, around this absorption tower, so this will be GNP plus 1 plus L0, which is equal to G1 plus LNP. Let's call this the equation number 1. And if you take the material balance for ammonia, so let's consider ammonia as component A. So material balance for component A, so we'll get GNP plus 1 times YNP plus 1 plus L0 times the mole fraction of the ammonia present in this solution, so X0 will be equal to G1 times the mole fraction of the ammonia which is present in this gas stream, Y1, plus LNP times the mole fraction of the ammonia present in this outlet solution, this will be X and P. Let's call this the equation number 2. And we know that operating line is in the form of Y is equal to mx plus c, and equilibrium line is in the form of Y is equal to mx. So in order to get the operating line, equation should be in this form, Y is equal to mx plus c. And now let's focus on the degree of the freedom, because here we have two equations and we need to find that how many terms in this absorption tower are known and unknown. So we'll make a column, so these are unknown and these are known. So unknown in this absorption tower will be L0, which is the liquid flow rate, and this will be L and P, that the liquid flow rate at the outside of this absorption tower is unknown, and we also don't know the composition of the ammonia at the outlet, so X and P is also unknown. And the quantities which are known to us is G and P plus 1, that is the total amount of the gas flow rate which is entering the absorption tower. We know Y and P plus 1, that is the composition of the ammonia which is present in the total gas flow rate. we know G1, that is the gas flow rate at the outside of this absorption tower. We know Y1 and we know X0. And here if you find our degree of freedom is equal to unknown minus number of independent equations. So unknowns are 3 and our equations are 2, so degree of freedom is 1, and this is unsolvable. And in order to obtain an equation for operating line, we are gonna take the balance for inert. So if we draw the same absorption tower for inert, so here in this case, if this is the mixture of ammonia and air, so air is considered as inert, and here the pure water is considered as inert. So we can write the flow rate of the air inside the absorption tower, Gs, will be equal to GNP plus 1 times 1 minus YNP plus 1, and here we'll get Gs is equal to G1 inside the bracket 1 minus Y1, and here we have, let's suppose Ls, this will be L0 1 minus X0, and here we'll get Ls, which is equal to LNP inside the bracket 1 minus XNP. And here we are gonna designing of tree. So if we write this equation number 2 in this form, so GNP plus 1 can be written as Gs upon 1 minus YNP plus 1. So this will be Gs upon 1 minus YNP plus 1 times YNP plus 1 as it is, plus L0 can be written as Ls over 1 minus X0 times X0 as it is, which is equal to G1 can be written as Gs upon 1 minus Y1 times Y1 as it is, plus, and LNP can be written as Ls over 1 minus XNP times XNP as it is. And now if we closely look at this equation number 3, so this is the moles of solute, so YNP plus 1 upon 1 minus YNP plus 1 is equal to moles of solute divided by moles of solvent in gas, and XNP upon 1 minus XNP is equal to moles of solute upon moles of solvent and liquid. And now we are going to denote these terms by capital letters. So this will be Gs times capital YNP plus 1 plus Ls times capital X0, which will be equal to Gs times capital Y1 plus Ls times capital XNP. Let's call this the equation number 4. And now we are going to rearrange this equation, and we are going to bring this term on this side. So Gs times YNP plus 1 minus Gs times Y1, which is equal to Ls times XNP minus Ls times X0. If you take Gs common, so this will be YNP plus 1 minus Y1, and this will be Ls inside the bracket XNP minus X0. So if we take Ls over Gs, so this will be YNP plus 1 minus Y1 upon XNP minus X0 will be equal to Ls by Gs. And now we are gonna draw the graphical representation of this equation. So if we draw the graphical representation of this equation, so here we got Ls over Gs is equal to YNP plus 1 minus Y1 over XNP minus X0. So if we draw the graphical representation of this, so here we have moles of solute, that is ammonia, divided by moles of solvent and liquid, and here we have moles of solute or moles of solvent in gas, that is, this is capital Y and this is capital X. And suppose our equilibrium line is in this form, so this will be y star is equal to the function of x. It is important to note that the nature of this equilibrium line depends upon the system. So for our simplicity, we are going to consider this equilibrium line in this form, and we know that the slope, this is our slope. So if we draw our operating line like this, so the corresponding point will be y and p plus 1, and here we have x and p, and here will be our y1 and this is our x0, and the slope is given by ls over gs. ls over gs is equal to slope. It is important to note that as we increase the liquid flow rate, then the slope will increase. Means if we increase the liquid flow rate, the slope will eventually become like this, and if the slope increases, then the distance between the operating line and equilibrium line, the vertical distance between the operating line and equilibrium line will increase, and that will increase our driving force. So when ls is increased, it implies that the slope is increased, and this implies that the vertical distance, that is this distance, which is also called as a absorption factor, and this is our driving force, also increases. And when the driving force increases, then the number of trays required for the efficient absorption decreases. So when the driving force increases, this implies that the number of trays required for efficient absorption decreases. And here this is the graphical representation for countercurrent absorption. And now if we need to find the ls by gs minimum, so what we are going to do is, in order to find the ls by gs minimum, so if you we draw the graph of, this is x, capital X, this is capital Y, and this is our equilibrium line, and if we draw our operating line which touches this equilibrium line in this form, so this is our x0, this is our capital Y1, and here we have capital Y and p plus 1, and the point which touches this operating line, this corresponding point is called x and p max, and this point is also called as a pinch point, and at this pinch point the vertical distance between the operating line and equilibrium line is 0, so the driving force is also equal to 0, and the trays required for absorption tends towards infinity. And now in some cases we know that when the Henry's law is applicable, then the equilibrium curve will change into a linear equilibrium line. So if we draw this is a capital Y and here we have capital X, and when the Henry's law is applicable, the equilibrium curve will change into the linear equilibrium line, and here we have capital Y and P plus 1, and where this capital Y and P plus 1 touches this equilibrium line, the corresponding point will be called as X and P max, and in this case our operating line will be something like this. This is our x0 and this is our y1. So, and once we find the LS by GS minimum, then LS operating is equal to 1.2 to 2 times LS minimum, and in this manner we can find our LS operating. And now what we are going to do is, in order to find this number of trays, we are going to make the use of, so this is NP, that is number of trays required. We are going to make the use of the Crimser equation. This is also called as Crimser-Brown equation. And in this case, when the absorption factor, that is the slope of operating line divided by slope of equilibrium line, so we know that the slope of operating line is LS by GS, and the slope of this equilibrium line will be M, so divided by M, so this will be LS by GS times M. So in this case, when the absorption factor is equal to 1, then the number of trays required NP will be equal to YNP plus 1 minus Y1 divided by Y1 minus the slope of equilibrium line times X0. And when the absorption factor is not equal to 1, then our number of trays required NP will be equal to log of YNP plus 1 minus M times X0 divided by Y1 minus M times X0 times 1 minus 1 by A plus A to the power negative 1 divided by log A. So this was all the information regarding the absorption in the countercurrent manner. And now we are going to deal with what happens when the absorption is done in co-current way. So absorption in the case of co-current. Absorption in the case of co-current. In very similar fashion, we are going to draw our absorption tower. Let's call this our bottom as 1 and top as 2. Here we have G1 and here we have L1. This will be Y1, this will be X1, and here we have G2, Y2, this will be L2 and X2. Here Y1 is the mole fraction of the ammonia which is present in the gas, and X1 is the mole fraction of the ammonia which is present in very small amount in the liquid, and Y2 is the mole fraction of the ammonia at the outlet gas stream, and X2 is the mole fraction of the ammonia in the outlet liquid stream. And now in this case, if we take the overall material balance, so we get G1 plus L1 is equal to G2 plus L2, and if we take the material balance, for the component A, that is ammonia, so this will be G1 times Y1 plus L1 times X1 is equal to G2 times Y2 plus L2 times X2. Let's call this equation number 1, let's call this equation number 2. And now if we take the material balance for inert, so here I'm gonna draw the absorption tower for inert. So this is GS can be written as G1 inside the bracket 1 minus Y1, and LS can be written as L1 inside the bracket 1 minus X1. Here we have GS is equal to G2 1 minus Y2, and this will be LS is equal to L2 1 minus X2. And now if you write the material balance for inert, that is in this case here air is the inert in the gas and water is the inert in the case of liquid. So this equation will become, equation number 2 will become, G1 can be written as GS over 1 minus small y1 times small y1 plus L1 can be written as LS over 1 minus small x1 times x1, and G2 can be written as GS over 1 minus small y2 times y2 plus L2 can be written as LS over 1 minus small x2 and this x2 as it is. And this term is our mole ratio. So if we rewrite this equation, GS times capital Y1 plus LS times capital X1 is equal to GS times capital Y2 plus LS times capital X2. Let's call this equation number 3. And now we are going to rearrange this equation. So GS times capital Y1 minus GS times capital Y2 is equal to LS times capital X2 minus LS times capital X1. So GS, if we take common, this will be Y1 minus Y2, and here LS X2 minus X1. So if we write Y1 minus capital Y2 over X2 minus X1 will be equal to LS over GS. So capital Y1 minus capital Y2 upon capital X1 minus capital X2 is equal to negative LS by GS. That is, this indicates that in the co-current absorption process the slope of the operating line is negative. So here if we draw the graph of, here we have the mole fraction of solute by the, here we have the moles of solute by moles of solvent in liquid, and here we have the moles of solute upon moles of solvent in gas. And if suppose this is the equilibrium line, y star is the function of x, and here we get the operating line with a negative slope, that is negative LS by GS will be equal to slope, and the corresponding points we have, this is our Y1 and this will be our corresponding X1, Y1, X1, and this will be our capital Y2 and the corresponding point will be capital X2. And if we extend this line which touches the equilibrium curve, then here we'll get capital XC, that is the moles of solute upon moles of solvent which is in equilibrium in liquid, and here we'll get the corresponding point, here we'll get capital YE, that is the moles of solute divided by the moles of solvent which is in equilibrium in gas. So this was all the information regarding absorption in the case of co-current and countercurrent processes, and we'll meet in the next video with some more concepts